Everyone, so we're going to continue talking about the gravitational force. And in particular, we're going to talk about, we're going to kind of do a little bit more with the 101 method. So we have to be very careful when we change the size of an object because there's something that I've been ignoring that technically also changes. If you take a small sphere, let's say a metal ball, and then you have another ball that is three times bigger, are, are they going to weigh the same? No. It turns out that if we increase the size of something and we're making sure that whatever it's made of remains there, technically we are also changing its mass because obviously there's more of it. So I've been ignoring it before in some of the scenarios where I said like, oh, if we imagine we made it bigger, we made it smaller. Um, so we actually have to find a way to figure out how changing the size of something ends up affecting the mass later on. So what we're going to do is we're going to use density. We know that density is equal to mass divided by volume, right? And we also know that for most of the objects that we're talking about, at least, volume of a sphere is given by the equation 4/3 pi r cubed. Now, I don't really care about this 4/3 pi part. What I care about is, I'm actually going to cross out. What I care about is that V is going to be related to r cubed. So if I rewrite this equation, m is equal to density times the volume, then if my density is remaining the same, since volume is proportional to r cubed, that tells me that m is proportional to r cubed as well. This is the relationship that I'm going to use anytime I change the size of something while keeping the density the same. I can also use this for when I do change density. I just would have to make sure that I include a row right in front of the r. So well, let's try it for these. So pause the video, work self, and we'll go over in a second. All right, so for part A, the mass is going to change this time. So I said before, like, oh, mass never changes, but remember, I'm physically changing the object now, so the mass has to change. So I'm going to use that relationship that mass was proportional to r cubed. Again, because it's coming from the density equation. I know that r is being doubled, so I put that in. So 2 cubed equals 8. So that means that my new mass is going to be 8 times the original mass. One thing to note is when you solve in terms of things like this, like 8m to represent 8 times the another variable, I always recommend making sure that you have them next to each other. If you had it where it was spaced like this, then this would end up being a unit. So just keep that in mind. This is a number multiplied by a variable. This is a number measured in some unit that's capital M. All right, so for part B, I want the gravitational acceleration on the surface of the sphere. So I'm going to use the equation g m over r squared, since that's that acceleration of gravity. I'm going to plug in the mass being changed by a factor 8 and the distance being changed by a factor 2. Plug those in, and I end up getting 2g. So I end up doubling my acceleration due to gravity. If I did not take into account the increase in the mass, I would have gotten 1 over 4g. So completely different from what I would have done had I not included the change in the mass. Here's the next one. Pause the video yourself. I'm going to go over in a second. All right, so for the first part, determine the mass of the sphere. I'm going to do the same thing I did before. I used the proportion mr is proportional r cubed. Plug in 3 for r. I get 27. So my new mass is going to be 27m. Finding my weight, I'm going to use the force of gravity equation. I'm going to plug in 27 for the mass of the Earth. My mass stays the same, and the distance increases by a factor of 3. So that means that in total, I end up changing my weight by a factor of 3. So it's going to be 3 times my original weight. Well, my original weight was 100 newtons, so now I'm going to weigh 300 newtons. All right, and I think this is going to be the last one. So pause the video, works off. I'm going to go over in a second. All right, so for this one, do the same thing, except here, one thing to note, uh, there's something different. It looks a lot like the last problem, but they mention now that the density is doubled. You want to make sure that when you're doing these problems, that you're constantly trying to compare it to another question that you've done before. So before we did m is proportional to r cubed. I can't do that anymore because that was assuming that the density remains the same. It's not remaining the same here. It's increasing as well. So I'm going to have to actually include this in with my r term. So now I have m is proportional to rho r cubed. Plugging my numbers in, that pretty much density and the radius all double. And I'm getting that my new mass is going to be 16 times the original mass. With this, I can then find my new weight using, now it's pretty much the exact same method I did last time. Put 16 in for the mass and 2 for the radius. I get 4 times my original weight, so that means my new weight is going to be 400 newtons. All right, and that's pretty much it for the 111 method. That's actually the hardest part. Uh, we'll see it pop up in other equations. Another one that's really common with is circular motion. I didn't include it in there, but that's just because I wanted it more for this, since there wasn't really much to talk about with this one. But technically, you can use it for any equation where you have two terms being set equal to each other. What I mean by that is, if you wanted to, you wouldn't be able to use it for the equation x equals x naught plus v naught t plus 1 half at squared, since there's too many terms. But if it turns out that x naught and v naught are 0, then this simplifies to 1 half at squared. Now I have one term being equal to another term. And then I could use the 1-1 method to see, if I change the time by a factor of 2, what happens to x. The only thing that you'd have to be careful of is if you used it on here, this constant is ignored. Just like how we're ignoring the 4/3 pi in the density equation, we would ignore every constant that we see. All we care about is how the terms are being affected. Oh, let me actually get rid of this. So one thing that we want to actually talk about is this thing called the gravitational field. So the gravitational field is the area of effect around an object where gravity exists. Now, I mentioned initially when I first talked about the force of gravity that it is an infinitely long force, meaning as long as you exist and you have mass, there is a gravitational force between you and any other object in the universe, regardless of how far away it is. Whether you're talking about you having a gravitational force with someone on the ISS, or you to the moon, you to Pluto, or to Alpha Centauri, or to the Andromeda Galaxy, there is technically a gravitational force, and therefore there would technically be a gravitational field caused by that. It's insignificant, so that's why we don't normally worry about it. But the strength of the gravitational field, we actually already did that. That's little g. Little g is the acceleration due to gravity, but it's also sometimes called the gravitational field strength. So we already have the equation that we could use to figure out the strength of this gravitational field around a planet.
Besides just figuring out the strength, you also have to know what the diagram around around an object would look like. It's easy enough. Basically, what you do is you just ask yourself what direction is the gravitational force. So, if you place an object anywhere around the Earth, the lines always go towards the Earth. Therefore, the field lines would go towards the Earth. That's pretty much it. There's just a few rules that you have to make sure that you follow. First, gravitational field lines never cross. It is impossible for field lines to cross over each other because this is just telling you the net effect of the forces that are acting on you. Gravitational field lines are always going to be attractive, meaning that all the lines always go towards an object. So because we're always attracted to the Earth, all the lines will go towards the Earth. And then last one is that the denser the line, stronger the field. Now, the way I usually refer to this, because for the most part, this is such a small, minor thing that you're probably not gonna recognize that, or you're not gonna remember it on the data test, and you might need to remember it some other way. What I usually do is I relate this to topographical maps that you might have learned in Earth science. If you recall, you could have these lines that kind of represented uh, altitudes and heights on some section. So, like one line would represent 10 meters in the air, 20, 30, and 40. Just like with the gravitational field lines, these lines would never ever cross. That wouldn't make sense because these are talking about heights. It's impossible for something to be both 10 meters in the air and 20. Gravitational, I mean, there was no directions with these, but one of the other things that you remember is that the lines that were very close together always told you how steep the hill was, essentially. The same idea applies here. The denser the lines, the closer the lines are together, the stronger the field. So these are what the gravitational field lines around the Earth. If we're looking at the Earth itself, as a whole, the field lines kind of go concentrically inside, or I should say, radially inside. And then on a flat surface, if we're looking at the surface of the Earth, because for the most part, the Earth is flat, it's zoomed in so much, the field lines are pretty much parallel. If we use that same idea from before, we can already see here that uh, the field lines very close to the Earth are much closer than the field lines further away. And this makes sense based on our equation that the farther we get away from the planet, the weaker the gravitational field strength. And then over here, we end up having that these lines are parallel, which again makes sense with what we know that on the surface of the Earth, the acceleration of gravity never doesn't really change. It doesn't matter if you're on the ground or up in a building, the gravitational field strength is still 9.8 meters per second squared. So it makes sense that the field lines would be essentially parallel. So that's pretty much it when it comes to the gravitational field. Again, need to be able to plug in to figure out the equation and be able to, see what the diagram looks like. Now, there is one small minor thing that I want to mention, and it's more of extra flavor. So, this virus is to say that this is not something you need to know for the AP, but it's interesting to know. Basically, what happens if we take this idea of gravity and the gravitational field strength to its maximum? Now, Einstein actually made his big claim to fame with general relativity, which basically looked at the effect of gravity and mass in relation to other things. In particular, what he found was that what we consider the gravitational force isn't really a force like the other three fundamental forces. It's actually the reason why it's so tough to incorporate it to all the other forces is that it's more of a bending of space time. That essentially a massive object will warp the space around it, and that warped space will actually cause objects to kind of fall towards it. The go-to way to visualize it is imagine placing a bowling ball, something heavy, onto a trampoline. When you put the bowling ball on the trampoline, it causes the trampoline to distort a bit, to bend downwards into the bowling ball. If we place a smaller ball onto the trampoline, the ball would end up falling into that little divot caused by the bowling ball, and it would make it seem like it's being attracted to it, as if it's attracted by the force of gravity between them. So that's kind of what's going on in the universe and outside into space. Is that these planets, these stars, these solar systems and galaxies are all bending space around it. Uh, the reason why this is actually important is because it actually results in a really weird effect of mass bending light. Now, if we go back to the original definition made by Newton, Newton said that the equation, Fg equals gm1 m2 over r squared, basically held true that any objects of mass exert a gravitational force on other objects of mass. But light is not an object of mass, it's massless. It is just a form of energy, essentially. So, using our typical Newtonian understanding of gravitational forces wouldn't really explain why light would end up bending because of, being around a massive object. And yet, scientists, astrophysicists, see this all the time. And this is actually a way that they can determine how massive an object is based off of the distortion of the light caused by it passing by some known object. It's also how we're able to find, black holes and such. So, uh, this is something that we really only see at very massive scales. Uh, on a planetary scale, or at least a smaller planetary scale, the amount that light bends isn't really that much. Now, there's another interesting thing is, if we keep going beyond this, well, if a massive star, let's say, can bend space enough to bend light, is it possible for it to bend light so much that it actually can't go past it, that it just kind of falls towards it, attracted to the object? And yeah, that's what a black hole is. A black hole is something that is so dense that the light around it ends up falling towards it and not going to be able to come out. Um, Now, there's a lot of really weird things that happen around black holes, and then there's also different types of black holes. So I'm not going to go into all the nitty gritty, but some interesting things are things like when you near a black hole, there's time dilation. That time changes differently based off of how close you are to a black hole versus other. So, for example, as you get closer and closer to a black hole, time for you starts to slow down a bit, meaning that your perception of, a year, let's say, as you get closer to a black hole, would be different to someone else on Earth who would actually might experience maybe 5 years during that same time period. Um, it's actually pretty interesting that one theory is that when you fall into a black hole, that the moment you pass over the event horizon, you end up experiencing the entirety of the rest of the universe within the fraction of a second that you're still alive. It will be like the last thing that you see. Some other interesting things is that we all know that light falls into a black hole. Nothing that goes into a black hole leaves. However, that's not the full story. Apparently, it turns out that that's really only true for stationary black holes, but some black holes are considered rotating black holes. And rotating black holes end up acting very similar to whirlpools in the sense that if you kind of swim in or fly into a black hole within the direction that it's rotating, you can actually continue with that speed, gain speed from that rotating black holeness, and then kind of use it to slingshot your way out. There are theories that that if there are civilizations beyond us, a lot of them are probably using black holes as a form of energy or even as a place to survive. And a lot of that comes from being able to take advantage of these rotating black holes. So this entire idea of gravity really goes down a very dirty, very complex rabbit hole. But it is extremely interesting. So I always recommend that, if any of this kind of interested you, definitely watch some, YouTube videos and do some stuff where you can see a lot of these other oddities with gravity. Now I'm going to leave it at that. That's going to be the last thing I talk about with the gravitational forces. What the next video is going to focus on is relating these two topics that we're talking about in this unit: circular motion and gravitational forces. So just to recap, the main thing that we want to go over was how the 1-1 method can go more complex, when we change the size, and how that could affect the mass. And then we also talked about the gravitational field, being able to calculate it as well as being able to draw it. That's pretty much it. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.